All right, we start here with chapter 2 and section 1. We're going to define the derivative of a function. So in this section, we're going to see the definition of derivative. We're going to see notation for derivative. We're going to see the relationships between the graphs of f and a function f prime. We're going to graph the derivative from data, and we're going to see what one-sided derivatives are. So we begin with 2-1-1 and the definition of derivative. You see there's a lot of vocabulary here. We're going to define the derivative of f at a point A. We're going to define the general derivative. We're going to find what it means to be differentiable, what is a differentiable function, and what is a derivative at a point. So a lot of new vocabulary here, and we're going to get started like this. At the end of chapter 1 in section 4, we defined the slope of a curve y equals f of x at the point where x equals a to be this. That slope m is the limit as h goes to 0 of the difference quotient. We defined that at one point, the difference quotient. So from this point forward, we are going to refer to this slope as the derivative of f at a. It's the derivative of a function. The limit as h goes to 0 of the difference quotient at some x equals a value is this limit that we're already so familiar with. In this section, we're going to investigate the derivative not as a slope at one particular point, but as a function, as an entire function derived from f by considering that limit at each and every point along the domain of f. So I just want to emphasize here, the derivative can be seen as a function if we think about the slopes not at just one point, but at every point in the domain of f. So a little further with derivative. The derivative of a function f with respect to the variable x is the function f, and it looks like f apostrophe, but we're going to pronounce this f prime, whose value at x is this. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Notice we replaced the letter or variable a with an x to indicate that we're thinking about this slope not at one point, but at all of the points as an entire function. And this derivative, this is the derivative as long as that limit exists. One note here, the domain of f prime, which is the set of all points in the domain of f for which that limit exists, might possibly be smaller than the domain of f. So just because the function f is continuous somewhere does not necessarily mean that it is differentiable or has a derivative. Speaking of differentiable, if f prime exists, we say that f has a derivative, or we call it differentiable at x. And a function that's differentiable at every single point in its domain is a differentiable function. So if something is differentiable, you can find its derivative. Here is a first example for us. We want to differentiate, that is, we want to find the derivative of this function f of x is equal to x cubed. So we get started with f prime of x. That's going to be equal to the limit, as h goes to 0, of course, of f of x plus h minus f of x all over h. This is the definition of derivative. So then let's apply it. The limit as h goes to 0 of, we're going to plug h or x plus h into the function. So that's going to give us x plus h quantity cubed minus f of x. So that's the whole function minus x cubed, and that's all over h. Next, we're going to expand the limit as h goes to 0 of x plus h quantity cubed expands into x cubed plus x squared h plus, actually it's 3x squared h plus 3xh squared plus h cubed, and then minus the x cubed from above, all over h. Now I notice here that x cubed minus x cubed zeroes out. And I also notice that the remaining 3 terms all involve an h. So I think we'll factor that h out. So now we have the limit as h goes to 0 of, factor out the h, have left over 3x squared plus 3xh plus h squared, and that's all over an h. Well, since we factored out that h, it's going to cancel with the one below, and that leaves us with then the limit as h goes to 0 of 3x squared plus 3xh plus h squared. So this is a polynomial, and we know that polynomial limits can be found by direct substitution. So that means now we can replace all of the instances of h's with a 0. So we have 3x squared plus 3x times 0 plus 0 squared, and that leaves us with 3x squared. That's the function we're calling f prime, the derivative of x cubed. So let's extend this definition of derivative just a little bit. We find the derivative at a point where x is equal to a by taking the limit as h goes to 0 or approaches 0 of slopes of secant lines, as we see in this familiar diagram here on the left. But if we relabel that picture, we can come up with an alternate formula for derivative by using the same secant slope formula. So let's talk about the labels. When we've drawn this graph before of some arbitrary function f, and we've labeled one point A, and then said we have some space between that point and the next one, and that space is h, which means that the following point is a plus h. Then we label the associated y values of f of a and then f of a plus h, and we construct our change in y over change in x by saying the y value f of a plus h minus the y value f of a over the x value a plus h minus the x value a, and that gives us the difference quotient f of a plus h minus f of a all over h. Now, if we relabel, I'm going to write that here. If we relabel, we can have a new diagram. We can have a, the same point, a comma f of a, but rather than saying there is a space between the 2 points here that we will move closer and closer, what we're going to do is label the second point as x. And that means its associated y value is f of x. And we have a new formula for change in y over change in x. It looks like f of x minus f of a, there's the y minus y, over x minus a, there's your x minus x. And the intent in both of these diagrams is the same. We want to take the second point and move it along the curve until it gets closer and closer to the first, so that our secant slope starts to look like a tangent slope, and we know the tangent slope is the derivative. So in the first diagram, we send h to 0. In the second diagram, as we move the second point closer and closer and closer to the first, what we want to do is move the point x toward a. So with that in mind, here is an alternate definition of the derivative at a point. The derivative of the function f at the point x equals a is this limit. F prime of a, there's the point, is the limit as x approaches a, that's what we saw in the last diagram, of the difference quotient f of x minus f of a over x minus a, provided again that that limit exists. So we can use this alternate definition in this way. After we find the derivative at the point x equals a using the alternative form, we can find the derivative of f again as a function by just applying the resulting formula to some arbitrary x in the domain. In other words, what we're going to do is we're going to replace a in the derivative with x. And that will give us the derivative as a function. So here is an example of that. We want to differentiate. Again, differentiate means find the derivative. Differentiate f of x is equal to square root of x using the alternate definition. So here we go. We say f prime of x is equal to the limit as, not h approaches 0 this time, but as x approaches some arbitrary number a, of the function f of x minus f of a all over x minus a. So let's use this function now and make this a little bit more real. So the limit as x goes to a, f of x is square root of x minus f of a is the square root of a all over x minus a. Now, we cannot simply just plug in a for x like we do on many other limits where direct substitution works. Here, that would yield, well, root a minus root a, so it would get us a 0 on top, and it would be a minus a on the bottom, and that's another 0. And this isn't 1, it's not 0, it's not undefined, it's actually something called the indeterminate form. And that means, hey, we really don't know what that is, but there's probably something else we can do. So with that being the case, we're going to try something else. And we should remember from some day of algebra using a method called multiplying by a conjugate. What we're going to do here is find the conjugate of root x minus a, or root a, which is root x plus root a, and multiply the denominator by the same. That way, effectively, we're only multiplying by a factor of 1, since root x over root a, or sorry, root x plus root a over root x plus root a is equal to 1. So let's continue this a little bit. The limit as x goes to a of, well, let's perform our multiplication on top. Root x times root x is x. And minus root ax plus root ax, that kind of zeroes out the two middle terms. And then we're finally left with negative root a times positive root a, so that's minus a. This is on bottom, or this is on top of a fraction with x minus a times root x plus root a on bottom. And you may notice that the factor of x minus a completely cancels, leaving a 1 in the numerator. So now this becomes the limit as x goes to a of 1 over root x plus root a. And as x approaches a, we can now replace this x with an a and have 1 over root a plus root a, or 1 over 2 root a. So there's the derivative at an arbitrary point a. But if we replace that a with an x, we have now f prime of x is equal to 1 over 2 root x. And there's our derivative of the function f of x, derivative f of x equals the square root of x. So there is the definition of derivative, an alternate definition of derivative, and an example used of each type. I will see you back for video 2.